And first, let me welcome everyone to this webinar. And thanks everyone actually to take the Thanksgiving holiday. And before that, and thanks for your time actually to attend this webinar. So we have actually have close to 90 people signed up for this meeting, and I'm sure they're going to join us very shortly. And let me just introduce the webinar today. So it is a joint webinar between CACA, which stands for Chinese American Chromatography Association, and MacMod. So CACA was formed on May 12, 2008, and I think that on the before the webinar you see the website of the CACA. And so that was the starting 2008. So our mission is really to focus on sharing technology information in areas of separation science, and also to provide network to members to share experience and to help each other in the career development, and also to provide a forum for the interaction. So we do have regular webinars as well as workshops, and mainly at our workshop mainly at the HPLC and the Pecan. So if any of you are interested in join us, and please visit our website, and or you can just contact any of us at the CACA. And we also have a WeChat for those Chinese. I think we like to use WeChat. And MacMod is a company, and so they are doing advanced chromatography by using state-of-the-art of technology, including software and as well as in-depth knowledge of chromatography to help the customer to optimize chromatography separation. MacMod has been in business for many years, and Jeff is their representative for this meeting at this webinar. So let me also introduce our distinguished speaker, Dr. Alan McCoy. And Alan is a Global Business Development Director at Advanced Chromatography Technologies. And Alan has wealth experience on both academia as well as industry, working at the AstraZeneca and GSK and Pfizer. Then later in 2012, Alan joined Advanced Chromatography, and his experience include new technology development as well as to promote the science. And so he is a frequent speaker at the various international meetings. So today, Alan is going to talk about accelerating new HPLC and HPLC method development strategy by leveraging selectivity, and also how to use a unique C18-based stationary phase. And hopefully, we all learn, from Alan. I'm pretty sure, he's going to give a very exciting technology. So we are going to learn how to utilize chromatography selectivity to optimize resolution, and also to optimize, the HPLC, UPLC development workflows. So by the way, my name is, just for those folks that don't know me, I'm Nai Dongwen. I'm work at Johnson & Johnson Springhouse. So with that, I'd like to have Alan to start his presentation. And Joe, just one housekeeping. In case you get kicked out from the meeting, don't get panicked. Just sign in back, and I think we will be there. Okay, so those things occasionally do happen, but hopefully it won't happen today. Thank you.
Okay, thank you very much for that very kind introduction, and welcome everybody. Thank you for logging on to this webinar across your lunchtime in the US. So as I was introduced, my name is Alan, and today I'm going to talk to you about a very important concept in chromatography, which is selectivity. I'm also going to talk about method development activities and how we can wrap these two things together, and also I'm going to talk about how we design stationary phases to maximize selectivity by the way that we put together the different stationary phase chemistries to maximize selectivity for our separations to give us resolution of the compounds of interest. You can contact me at the email address on the screen at the moment, and I hope that these slides will also be available in PDF form after this webinar, and also this webinar is being recorded as well, so you can listen back if there's more information or if you want to listen to the webinar again. So today's talk, I'm going to talk about selectivity. I'm going to talk about how we do method development, the different workflows, the different tasks that we have in the method development activity. I'm going to say and talk a little bit about how we design new stationary phases to maximize selectivity, and I'm going to talk about selectivity diagrams. So these are very useful diagrams in chromatography. They help us understand which columns are different to each other and which columns are similar to each other. And these diagrams can also help us choose different types of columns to maximize selectivity in our separations and try and achieve our desired method as quickly as possible. So first of all, what is selectivity? This is the classic description of selectivity you can see on your screen now. It is often denoted by the symbol alpha. So alpha is the ratio of retention factors between two adjoining peaks. This is what people know as selectivity. Sometimes selectivity is known as the separation factor or the separation selectivity, or even it can be thought of as peak spacing. Now, why does this matter? Well, what we have on the slide now is the resolution equation. What we're trying to do as scientists is resolve compounds from each other. And we can see in this form of the resolution equation that there are three components. There is an efficiency component, a selectivity component, and a retention component. Now, when we look at these three components in the resolution equation, how do we understand which is the most powerful term? Obviously, efficiency is important. We all like to see nice, efficient peaks, narrow peak widths. It's good for sensitivity, good for integration. But if we look at the equation, we can see that resolution is proportional to 1/4 the square root of n, the number of plates. So you need a very big change in efficiency to get a big change in resolution. Now, if we look at retention and the retention component in this equation, again, we can see that retention is obviously important in chromatography. If we don't retain analytes, we cannot separate them. And if we retain them too much, we never see them again, and that's not useful either. Whereas if we look at selectivity, selectivity really is the powerful term in this equation. If we look at the graph on the right-hand side, you can see resolution is on the y-axis, and on the x-axis you can see alpha, selectivity, n, efficiency, and k, retention. And you can see the relationship between alpha, selectivity, and resolution. It's almost a linear relationship. Selectivity keeps on increasing with respect to resolving compounds from each other, so it's a very powerful term in this equation, whereas we can see n and k plateau off to a certain degree. So selectivity really is the key to resolution, but of course efficiency can boost performance. So this slide is a very simple theoretical slide to try and help us understand why selectivity really is the central concept in chromatography. If we understand selectivity and which parameters affect selectivity, that means we can maximize the resolution of our compounds. So now we know selectivity is the most important term in the resolution equation. Which factors affect selectivity? Well, in fact, if you look across the different hardware and mobile phase and column parameters in chromatography, you can see that most things will have an impact on selectivity. And on the slide on the left-hand side, you can see we have isocratic separations, and these are in a list format, so a bulleted list. So the parameters at the top of that list have a bigger influence on selectivity than the parameters at the bottom of the list. And on the right-hand side of that slide, we can see gradient separations. So all of the parameters on the left are important for gradient chromatography, but there are a couple of other parameters we need to consider and how they influence selectivity. This includes the gradient steepness, It includes the apparent retention in gradient chromatography, which is described by the simple equation on the screen, and includes gradient time, flow rate, column volume, the gradient range, and a factor for the size of the analytes. Then we have dwell volume and we have column dimensions. All of these different parameters that I've listed have an impact to a greater or lesser degree on selectivity. Now what we must do as chromatographers is try and focus on those parameters which give us more impact for our separation, which maximize selectivity to give us the method that we need as quickly as possible. If we look at method development in an overall sense, we can see that typically it is multivariate. There are many different parameters that we can consider when developing a method. On the screen you can see 5 different boxes, and you can see that from a method development perspective we could start on the left hand side of the slide and we move slowly through each box looking at its impact on our separation and on the resolution of our compounds. So we can look at gradient times, we can look at temperature, we can look at solvent type, maybe we'll look at some different columns, and we can also look at pH as well. Now, of course, as we explore more parameters, our approach becomes more complex. We do more injections and it takes more time. However, we also generate more knowledge as well. Now, in an ideal world, we would want to fully explore all parameters across their range within that parameter to get a full understanding of the retention behavior of our analytes. But of course we're always time constrained. We always need a method as quickly as possible so we can move on to the next method development activity or to analyzing samples or whatever it is we're trying to do. So there are lots of different ones we can do to explore the effects on retention and also the resolution or selectivity of our analytes. Now, from a method development perspective, it would be great if we could reduce the number of parameters we need to examine. And of course we can do that if we consider the parameters and their impact on selectivity. We can remove some of the parameters that have less impact on selectivity, and this should speed up our analysis time, our method development time. Now for today's talk I'm going to focus on different properties of stationary phases. This column stationary phase has a big impact on selectivity, so choosing the right types of columns when we want to screen our samples to try and get a separation is really important. So today I'm going to talk about how we can choose different types of columns with different properties to maximize selectivity. Now when we're designing new stationary phases, and the example I'm going to use here is based on aromatic stationary phases, we want to bring together different types of chemical groups that can give us different interactions to help us separate our compounds of interest. Now if we take a simple benzene ring and we substitute onto this benzene ring different types of electron donating groups, and there are some examples that I've written there, you can see that we start to change the properties of that ring. Now you can see the example structure that I've put there has an alkyl chain on it, so this is similar to a phenol, a short chain phenol type stationary phase. And you can see that if we look at the electron distribution within this ring, this is an electron rich ring system. So the alkyl chain donates or pushes electrons into the ring system to give us a slight dipole across this ring and a slightly electronegative ring system. Now of course we can do the opposite to this. We can put onto this ring system different types of substituents such as electron withdrawing groups, and what I've drawn there is the classic pentafluorophenol type stationary phase. Now with those fluorine groups on this aromatic ring system, we create a moderate dipole across that ring and we create a slightly electron deficient ring system. It is obviously different in its properties compared to the electron rich ring system. So this is an example of how we can understand material characteristics to change the properties of the stationary phase. Now of course that's very interesting from a materials perspective, but we're interested in chromatography. How does this affect our stationary phase design? Well, what we've done with the stationary phases in the ACE portfolio is we've brought together the properties of a C18 ring system, which is the most popular stationary phase, very stable, very robust, low bleed, together with a phenyl type stationary phase, and that's what the C18AR product is. So this brings together the mechanisms of interaction of a C18, such as hydrophobic interactions, but also with the ring mechanisms of interaction. So that includes pi system interactions and a weak dipole, and also some steric selectivity as well. And the same on the right hand side of the slide here. We have a C18PFP stationary phase, which is bringing together the mechanisms of interaction of a C18 and a pentafluorophenol within a single stationary phase. So we're designing all of the benefits of these two stationary phases into a single stationary phase, but designing out the weakness of the short chain phenol and the short chain pentafluorophenol. So both of these phases have multiple mechanisms of interaction. They display low bleed profile, similar to a C18, but they're also 100% wettable as well. So if you're trying to retain those polar compounds, you can use these phases at very low or 100% buffer, and you won't get phase collapse or poor dewetting. So as an example of the chromatography for these phases, you can see at the top of the screen we have the C18AR stationary phase. Now this mixture is a mixture of 9 non-steroidal anti-inflammatory drugs, and you can see the bottom chromatogram is the separation using a short chain phenol stationary phase. Now under exactly the same conditions, if we analyse the same sample mixture with a C18, the middle chromatogram, you can see we get a different elution profile, and that's because the C18 stationary phase is dominated by hydrophobic interactions, whereas the bottom chromatogram, the short chain phenol, it has pi system interactions and a low hydrophobic interaction component. On the top chromatogram we have the C18AR stationary phase. This brings together the hydrophobicity of a C18 but with the aromatic interactions of a short chain phenol, and you can see we get a different elution order, we get full separation, and we get a different selectivity compared to the other two stationary phases. This is an example of rational stationary phase design, bringing together the best interactions from two different phases into a single stationary phase. And this example here is a C18PFP of methoxybenzene isomers. So these are regioisomer type analytes. So you can see from the top chromatogram we wouldn't expect to separate regioisomers with a standard C18, and that's exactly what we find. We see coelution. Now on a short chain pentafluorophenol, you can see we actually almost get a full separation, so that's not a bad separation at all on that hypersil gold pentafluorophenol. But with a C18PFP, we bring more hydrophobicity to the separation, we maintain the pentafluorophenol mechanisms of interaction, and we get a different selectivity and full separation of all those compounds. And the retention window is much broader. So again, another example of with the C18PFP, which shows how those additional mechanisms of interaction can help us separate very structurally similar compounds. Now other types of stationary phases we can design from a novel perspective as well. So this first phase I have here is a C18 amide. This is amide. This is a polar embedded phase, and you can see a couple of features of this phase that make it different to other phases that are available. First of all, you can see we have an extended spacer between the embedded amide group and the siloxane bond on the silica particle. Now this extended spacer provides improved stability to this stationary phase. The bleed with this phase is low. We have the embedded amide group, which gives us different types of interactions compared to aromatic phases and to alkyl chain-based phases. And then we have a C18 carbon chain, which gives us hydrophobic interactions. And then we have a stable cyanotype phase. So here we have an extended alkyl chain spacer with a terminal nitrile group. And we can still see very clearly the mechanistic interactions from that terminal nitrile, but we have a hydrophobic component to this cyano phase as well. And also this cyano phase is much more stable than traditional cyano phases because of the extended spacer. So there's very low bleed with this phase. So multiple mechanisms of interaction, designing out the weaknesses of phases that already exist to give low bleed, but both of these phases again are also 100% wettable. So this gives us a different selectivity by maximizing the selectivity in the phase design. As an example, here we have some polyhydroxyaromatic analytes, and you can see on the bottom chromatogram the separation with a standard C18, and then the top chromatogram under the same conditions you can see that embedded amide group is working hard to give us retention, a different selectivity, a different elution order, and full separation of these similar compounds. An example of different selectivity. And finally, we have the super C18 stationary phase. This has been designed to give a wide pH range of operations. So this is stable from pH 2 to pH 11. So it gives a nice opportunity to use mobile phase pH should you need to use it in developing your methods. As an example, here we have a low pH separation of this mixture of different compounds, pH 3, and if we use the same analytes with the super C18 but at high pH using ammonium hydroxide, these two chromatograms are on LCMS suitable buffers, you can see we get quite a different separation, a different elution order, showing you how pH can affect the ionization state of the analytes to give differences in retention. So this stationary phase is using its stability under different pH conditions to give us a different selectivity. So the different applications that I've shown you as I'm moving through this talk are all available within a complete applications guide. There are hundreds more applications available. You can order this from MapMod Analytical in the US, or you can send them an email and they can send you a hard copy of this document, or they can send you a PDF. So this covers many different applications from clinical and forensics, toxicology, the food and beverage sector, environmental, pharmaceutical. There's lots of LCMS applications in there as well. So there's many different applications and examples in this booklet. It's just a whole collection of application types. We've got a very nice application index in there and also an analyte index too. So if you're trying to separate X from Y, you can very easily look up X or Y, and hopefully it should cross-reference to an example within this booklet. So how do we understand differences in selectivity between columns? Well, this on the screen now was first published by Uwe Neuer, the late Uwe Neuer, in 2006, and it's a simple but powerful approach to understanding if columns are similar or if they're different from each other. For method development, we'd like columns to be different to each other so that we can move peaks around in the selectivity space, give us different elution orders, and also if something's co-eluting, hopefully on one column, hopefully it won't be co-eluting on the second column that has different selectivity. So what Uwe Neuer discussed in this paper was that you take your column 1, you can see on the y-axis there, you run a certain method of your choice with your analyte mixtures and you note the retention times. You then take column 1 out, you put in the second column and you equilibrate under the same conditions and run the same method and the same sample, and you should get different retention times. You then very simply plot the retention times against each other and you generate a correlation coefficient, an R² value. You put that into the equation that's on the screen and you generate a selectivity descriptor value. And it ranges from 0, which means that the columns are identical to each other, to 100, which means the columns are completely different to each other. So selectivity values from about 8 upwards indicate that the elution order and the selectivity of the two columns should be different enough to each other to be suitable for method development. You can get much larger selectivity values if you change multiple parameters or if your column chemistries are very different to each other. So let me show you some examples. So first of all, we have generated selectivity data on the different columns that I'm going to discuss. And we've used a mixture of 45 different acids, bases and neutrals, small molecules, to challenge the columns to generate the retention times to plot against each other to calculate selectivity values. These 45 different analytes represent a broad range of physicochemical parameters, different log Ps, different pKa's, acids, bases, neutrals, vitrionics, phenolics, and they essentially describe the small molecule space. So the data I'm going to show you is very suitable for small molecules. Now if you're interested in HPLC or SFC or large molecules, you would use a different molecule set. But for this particular columns and this selectivity data I'm going to show you here, this is for small molecules. So selectivity values between 0 and less than 8 means the columns are actually quite similar to each other. So you're not going to see very much difference in the retention times between the two phases. And this is a classic example that you see when some analysts are using a C18 for their analysis and they take the C18 out and they put another C18 in from a different vendor. Now what you're actually doing there is using two columns with very similar selectivity, and you can see on the screen there the data that I've showed you. C18 from vendor A at low pH in acetonitrile as standard gradient versus the retention data from a C18 vendor B, low pH acetonitrile gradient, exactly the same method. You can see that the correlation coefficient is very high, which means the selectivity value is very low. So using C18 only, or two C18s from two different vendors for method development, is not very helpful because you get very similar elution. Now the selectivity values greater than 8 and less than 30 are useful to us because you start to see changes in the retention time of analytes and also elution order changes. We're starting to see scatter in the data. So you can see here the 45 different analytes, and we have on the y-axis an ultra-coarse superphenyl hexyl at high pH in methanol versus an ultra-coarse superphenyl hexyl high pH in acetonitrile. So we've only changed the organic solvent here, but you can see how the organic solvent influences selectivity. We're starting to see a lower R² value giving us a higher selectivity value. So typically you would observe these moderate selectivity values when you change a variable, such as the solvent, or if you compare different types of stationary phases. You'll start to see a C18 versus a C18AR, for instance, or methanol versus acetonitrile. And as an example, you can see here we have a scatter plot and the chromatograms. You can see there the ACE Ultra Coarse Super C18 at the top, and this is a 23 component mixture, and you can see at the bottom the ACE Ultra Coarse Super Phenyl Hexyl. So we've changed the bonded phase type, and you can see the red rings that I've put on the chromatograms. We're seeing differences in the retention times, differences in the elution order of the components due to differences in selectivity. Now we can also get high selectivity values as well, greater than 30. Here we see significant changes in retention and or elution order. So you can see from the graph that I'm showing there, there's really quite scattered for the 45 analytes, a low R² value, which gives us a very high selectivity value. And I'm showing you there a value of 81. Typically you would see this when you change multiple parameters, or in particular if your compounds are ionizable, then if you change pH, e.g. a low pH versus a high pH. As you change the ionization state of your analytes, as they become charged or uncharged or ion suppressed, then it has a massive effect on their retention in reverse phase chromatography. But of course, low pH versus high pH, we must be using a suitable stationary phase, one that can be used at low pH and high pH. So here we have a low pH versus high pH separation with two very different elution orders for this 11 compound mixture, and you can see the selectivity data there at 83 showing a high degree of scatter for these two different chromatograms. So that's the same column but two different chromatograms. So why a stationary phase is useful, different stationary phases? Well, typically we're trying to understand what's in our samples. So on the screen at the moment is a degraded sample, and if we count up the tops of the peaks, we can see there appears to be 22 peaks. But is 22 peaks everything? We can see there that some of the peaks are quite broad. There might be other components co-eluting with some of those compounds. Now we can see that that first chromatogram is using a C18 based stationary phase. So the mechanism is dominated by hydrophobicity. If we were to use a different stationary phase, such as a C18 PFP, this has a different mechanism of interaction. Here you can see we have hydrophobicity, but we also have the pentafluorophenol mechanisms, pi system interactions, dipole interactions, shape selectivity. And if we run the same sample, the same degraded sample, under exactly the same conditions as in the yellow box already on the screen, we get a very different elution order. In fact, we appear to get now 28 peaks. So we're seeing significant differences in the number of components and the elution order from this particular sample. So this is a good example to show how different stationary phases affect selectivity due to the different mechanisms of interaction. From a method development perspective, this is very powerful. If we can keep the conditions the same, but use different stationary phases as our selectivity tuner, it can help us understand our complex samples and hopefully develop methods faster. In this particular example, we have a 16-component mixture at a low pH using a C18AR in acetonitrile. And we can see we've got some different areas of co-elution, and yet if we change the solvent using the same column, the same conditions, the same mobile phase, you can see we get very different elution order and complete separation of this 17-component mixture. So now we're using the type of solvent as a selectivity tuner. So in the first example I showed you different stationary phases. In this example it's different solvents. But what we're doing is affecting selectivity. We understand that the stationary phase type and solvents are important selectivity modifiers, and that's what we're doing here is changing that selectivity with a selectivity value of 15 between these two different examples as I'm showing you here. So how can we put this together for method development? Well, here we have a 6-column switcher. This is what we use in my own lab for method development. So we can put together 6 different stationary phases. Some people use 3, some people use 2. I have a 6-column switcher, so we use 6 with different types of stationary phases. And you can see we've got different phases from a standard C18 to the C18AR, the C18 PFP, a super C18 which has a slightly more hydrophobic surface, the polar embedded C18 amide, and the stable cyano-ES. All of this is in with acetonitrile at low pH. And if you think about the different selectivity descriptor values, we can calculate all these different descriptor values, and I'm showing one example here, selectivity value of 26. Okay. Now, of course, this is a useful method development platform. We've got different columns with different selectivities, and we can prove that because we can challenge the columns under these conditions and show that the selectivity is different. And I'm going to show you a specific method development example using this approach. However, we can take this one step further. I showed you previously that solvent was very powerful for affecting selectivity. So what I've now done is combine the 6 different columns with methanol and acetonitrile, and this is my standard method development platform that we use every day in my own lab. And as an example, you can see their selectivity value of 37 between the C18AR in acetonitrile and the C18 amide in methanol at low pH. So you can see, and you can imagine how complex that diagram would be with all the different dotted lines if we were to calculate all the different selectivity values, which we have done. But what I'm trying to show you here is a rational method development platform based on 6 columns and 2 solvents. It's a screen that we can use in our labs, highly automated, to give us options for method development. So the 5 boxes that I showed you originally, we can now collapse down to 2 boxes because we've got columns, there are 6 columns, and we have 2 solvents, acetonitrile and methanol. And I know that both of these maximize selectivity because I've already done that work to prove it from my selectivity descriptor values. So we no longer have 3, 4, 5, 6, whatever parameters, it's a much longer method development workflow. I've now got 2 because I know I'm going to explore the selectivity space using column selectivity and 2 different solvents. We're maintaining that rich data and information that I showed you at the beginning. So What does it look like? Well, this is in my lab. This is exactly what it looks like. This is our method development platform. You can see here this is a HPLC system, and we have 6 ace columns in our column oven. The switching valve at the bottom there. This is our standard platform that we do. We always start our method development on. So how do we do method development? I'm going to do a step-by-step example to finish up. So first of all, I've split this into 4 different steps. I'm only going to talk about the first step today due to the time. So typically most people will do some scouting runs with general starting conditions to get an idea of what's in their sample and understand the retention behavior of the analytes in their sample. So most people do a broad scouting gradient run. How do you know at acidic pH? How do you calculate your starting conditions? Well, hopefully you've decided on the column platform to use. The column platform, the dimensions that I always recommend for HPLC is 100 by 3mm columns. These are a good, robust platform for method development. They also offer you the ability to go smaller if you want to go faster, or to go bigger if you want to use the method under HPLC conditions. So here we have some standard conditions. There's a flow rate of 1.2 mils a minute, which is appropriate for a 2 micron type particle, a gradient time of 5 minutes, a gradient range of 5 to 95. We can calculate the column volume, and the K-star values that we're using in general arm wavy type from books and so on is that your K value should be greater than 2 and less than 20. Some books and manuals and guides say greater than 5 and less than 10. It really depends which author you're reading. So for me, I've used greater than 2 and less than 20, and you can see if we calculate the K-star values, they should work out in this range for us. Now the example I'm going to show you is using acetaminophen or paracetamol here in Europe. Now this particular example, you can see there is the main parent compound, and then we have these different degradation products and synthetic process-related impurities spiked into the sample at 0.5%. Now, normally I would always start a gradient run, a scouting run under acidic conditions, unless you know differently. And in this particular example, I do know differently because the compound 4-aminophenol, we can see from the log P value here, has a negative value, which means that it's very polar and will elute on the T0 at acidic pH. You can see the log D value at 5.5, it is less negative, and the log D value at 7.4 is actually positive. So this tells us by increasing the mobile phase pH, we should get better retention of this polar compound. But as a general rule, always screen under acidic conditions, pH 3 using ammonium formate, formic acid, typical type of conditions. For this particular example, I'm using ammonium acetate at pH 6 specifically because I want to retain 4-aminophenol. So the general scouting conditions are listed on the slide there. You can see there's nothing unusual or strange there. And of course we analyze our 10 compound mixture, and these are the data that we get with methanol. So you can see there at the top we have the standard C18, then we have the C18AR, the C18PFP, the super C18, the C18 amide, and the cyano-ES. Now you can see if we look at the green box to start with, we can see that peaks 1 and 4 co-elute on the standard C18. We get some separation on the AR, they co-elute again on the PFP, co-elute on the super C18. They actually switch order on the C18 amides, and then they're completely separated on the cyano-ES. In the red box we can see the selectivity between peaks 7 and 8. You can see that we've got full separation on the C18, the AR, the PFP, and also the super C18, and then on the C18 amide we get a switch in elution order. So peak 7 and 8 switch order on the C18 amide. So those differences and interaction with the polar embedded phase have given us more retention of compound 7. And then on the cyano-ES, we've still got a reversal in the elution order. So very interesting to see different selectivity values depending on the stationary phase. Don't forget these have all been run under exactly the same conditions. The only difference is the stationary phase. And then finally in the purple box we can see peaks 9 and 10 separated on the C18, co-eluting on the AR, separated on the PFP, partially co-eluting on the super C18, very well separated on the C18 amide, and very well separated on the SINE-OES. So we can see from this initial screening data that we have two options for complete separation of all 10 compounds. You can see that from the green ticks that we have the C18 amide and we have the SINE-OES, giving us options for a method to take forward for the analysis of samples for process-related impurities and degradation products for acetaminophen. Interestingly, if you look at the red box, this is where most people would start their method development. They would use a C18. And you can see that the issues that would have brought for most people. They would have had co-elution of peaks 1 and 4, and very just about separation of peaks 9 and 10. So the question you have to ask yourself is, if you'd started with that first chromatogram, what would you have done next? You would have started modifying the gradient, changing the temperature, started to do more injections, making small tweaks to your method to try and separate the 10 compounds in that mixture. Whereas using the screen that I've got in front of you, you can see you've got two options for complete separation because you've used different column chemistries. You've maximized selectivity for your screening runs. So this is for the methanol solvent, and we have the same data again, but this is using acetonitrile. So again, you can see we have the C18 phase at the top. We can see co-elution of peaks 8 and 9 this time. We can see a different elution order of the compounds as well. So now we're seeing the influence of acetonitrile as an organic solvent different to methanol. And you can see the C18AR, the C18PFP and the super C18 all provide complete separation of the 10 compounds. This time the C18 amide does not. There is co-elution, but the SINE-OES does. So from the methanol, the acetonitrile screen, you can see we have 4 options for complete separation. But again, most people would have started with C18, the first chromatogram. They would have had co-elution of peaks 8 and 9, and they would have started tweaking their separation. What I'm showing you here is a 6-column 2-solvent screen that was potentially give you 6 options for complete separation out of 12 chromatograms. That is the power of using different column chemistries in your screening protocols. This is the way that I always do method development in my lab. I always start with this screen, stand back, and then look at which one gets me closest to separation, and then I start using that to take forward. But normally, out of these 12 chromatograms, I get at least one option where everything separates. So this is a very nice platform for separation, hopefully giving you options for your method development moving forward to developing your final method. Now, the method development options that I've talked about are available in this guide as well. So this is available from MapMod Analytical, so they very happily send you the information. And what I've tried to highlight here, you can see on the second part, the right-hand side of the slide, are the method development kits. The 6 columns that we've designed for small molecule method development, you can see there as the advanced kit and the extended kit, the blue box and the red box. These are 3-column kits, and the great thing about these 3-column kits is they are available for the price of a single column. So you could buy a C18 from the advanced kit and we would send you the other 2 columns for free, or you can buy the super C18 in the second box and we would send you the other 2 columns for free. So for the price of 2 columns you would get 6 columns to set up a screen like I've described for method development, which I think is a great offer, and it's very powerful because they've been designed to maximize selectivity. If we look at the kits in more detail, you can see the different mechanisms of interaction, and you can see how we've got the 5 modes of interaction that I've described there: hydrophobic binding, pi system interactions, dipoles, hydrogen bonding, and shape selectivity. More stars means that that mechanism is stronger with that particular stationary phase, and you can see how the different kits are complementary to each other for different types of separations. So really trying to provide a solution for chromatographers to help them screen their compounds to develop methods faster. So just to finish up my presentation, to leave a few minutes for questions, hopefully what you've heard about today is how important selectivity is in chromatography. It really is a central concept. If you can understand selectivity, through your column choices and using different solvents, it can really help you get faster with your method development. It really can. Focusing on different column chemistries and maybe acetonitrile and methanol, a screening platform like I showed, really can help you get get methods much quicker from your method development activities. Hopefully what you've seen is that we've designed stationary phases to maximize selectivity. The phases I've showed you are complementary to each other. We've designed them to be within kits at a great price point so that you can use and leverage these different selectivities for your separations. What I showed you today was an example with acetaminophen and 9 additional impurities, and you can see how a screening column approach can be quite powerful. The only difference with a screening column approach is the stationary phase that you're using. If you keep the other conditions the same, you'll see then differences in retention and elution order, and hopefully that will help you with your method development activities. And what I showed you was basically an optimized method platform based on 6 columns and 2 solvents. I have many people that I work with who use 3 columns and 1 solvent, or 3 columns and 2 solvents. It really depends on what it is that you're trying to do and what you want to do in your laboratory. So I'm going to wrap up there and finish the talk. Hopefully that's been of interest to you listening to the presentation. I hope there was some stuff in there about phase design that was interesting. I hope there was some stuff in there about method development workflows that was also interesting to help you solve the problems that you face every day in your labs. And with that, I'll hand back to the admin and we'll open up for maybe a few questions. Thank you very much for listening.
Hello? Yeah.
So that's me done now.
Okay, great. Thank you, Alan, for the great presentation. And I think, thanks again for the expert opinions on the column selections. And, I was wanting to ask a question, but apparently as an organizer, I cannot type in the questions. I think you did a great job. And for me, and I always think, the selectivity is very fundamentally important for all the chromatographs. I mean, these days, I think we are so tend to just go to HPLC. I forgot about the fundamental importance of selectivity. And thanks again for bringing us back to the fundamental of HPLC. So there are a few questions. I don't know, Alan, can you see the questions on your screen?
No, I can't see anything.
Okay.
Are they typed in somewhere, or?
Yeah, they're typed in the question section. If you cannot see it, I can read for you.
Yeah, maybe you should read. I don't have a questions segment, so I can't see anything.
Okay. The first question is regarding to what is the maximum percentage of end capping groups that you can push into a silica foundation?
The maximum, so if I just repeat the question just to make sure that I heard it correctly, if that's okay. Yep. So what I heard was, what is the maximum amount of end capping that you can do on a silica column?
That's correct. Okay,
so the maximum amount of end capping is around about 50% of silanols. That has been demonstrated theoretically, academically, and also practically. So it is nigh on impossible to completely shield all silanols from secondary interactions. But what we have to do is actually, those silanols can actually be helpful for our separations as well. So we actually wouldn't want to completely shield or end cap completely a silica-based column. Some of those silanols, the different types of silanols that are there, are actually useful for interactions with our analytes and provide us with selectivity and therefore separation. So yes, so to answer the question, it's about 50% is the generally accepted number for the maximum amount of coverage that you can get in terms of silanols.
Very good, thank you, Alan. And the second question is, do you recommend any software for HPLC method development? And also, what samples do you use for initial column screen?
So Yes, I do recommend software. In our laboratory, we use two packages. We use ChromSword Auto 5, which is a system which is something that is very nice, very powerful, but also I've used for many years, I've used DryLab. For a long time I've used DryLab. I'm a big DryLab fan. It's a program that I grew up with essentially when I was being taught chromatography over 20 years ago now, and it's a program I'm very familiar with. So DryLab and ChromSword Auto. ChromSword Auto provides some additional features that are not available on DryLab, so we tend to use a balance of those two packages in my laboratory.
Great. Thank you, Alan, and a very good answer. The next question, do you recommend any particular column for sugar phosphate analysis? So far, this audience used the Helica column. So do you have any other column other than Helica column can be used for sugar phosphate analysis?
Interestingly, so for sugar analysis, there are some slightly older products which we found that we've used for different types of monosaccharides and disaccharides, trihaloses and stuff like that. If that's what the question is aimed at, we've used some Alltech columns, which we found very recently to be very good, even separating very closely, structurally closely related sugars such as glucose and galactose, which are typically very difficult to separate with certain types of columns. So we've actually used, like I said, this Alltech type column. If anyone wants the specifics of that column, I can email that or I can share that separately. It's a commercial product. It's from the Legacy Grace portfolio, but we found that to be an extremely good column for sugar analysis, if that's what the question's aimed at.
That's great. I think you have your email address available, and yeah, I think please send to Alan and the information. So he can provide the information back to you. And so it looks like there's a lot of interest on the analysis of polar compounds, and so there are also questions regarding to oligonucleotides and glycosidic metabolites and phosphates and so on and so forth. And so any particular recommendation, Alan, in terms of analysis of very polar compounds?
Okay, so most of the work that I've talked about here is for reverse phase type analysis, in which the retention of polars is always an issue. Now, in the 6 phases I particularly highlighted today, I'm going to just flick back just a couple of slides so the audience can still see this. The 6 phases that I highlighted today, the C18 PFP, is the phase that gives the most polar retention from the phases that I talked about today. And that's actually not a bad phase at all. It can be used in 100% buffer as well to really try and get retention of those polar species. However, we have to be realistic here. So if people are talking very polar compounds, then reverse phase is not the technique to use anyway. So there are other techniques that are probably more applicable, of which there's a lot of interest in HPLC at the moment, so hydrophilic interaction liquid chromatography, and in fact there will be very soon a new HPLC kit available from ACE for the retention of polar compounds, and this will also have worked examples of HPLC method development and how to develop a robust HPLC method. HPLC has a lot of problems because people feel it's not robust. Well, I've written a guide, a HPLC guide, which will be available when the product launches in the next month, and so you're getting a sneak preview here. And in this guide, I discuss how you can make sure your HPLC method is robust as reverse phase chromatography. And it's to do with the equilibration of the column before you begin your analysis and between injections if you're doing gradient HPLC analysis. But I don't want to talk too much about that today, but it is possible to get very robust HPLC methods. So just to summarize, you're always limited in reverse phase with how polar you can retain. The C18PFP is the one I would recommend for polar retention based on what I talked about today. If your compounds are even more polar than that, you possibly need to consider another technique. HPLC is one option, potentially ion exchange, chromatography is another option as well. But more or less people want to try and have a reverse phase-like separation, in which case C18PFP is one I recommend. But think about HPLC too. It is possible to get robust HPLC methods. I have a guide to help everybody coming out very soon.
That's excellent, and we have a common language. And as a matter of fact, I think Andy Abbott, who is also on our CACA committee, executive committee, so he is also, for sure is a HPLC expert. I'm not sure if he's online or not. So I think we have just a couple of minutes. So I would like to take the, last couple of minutes. First, thank Alan for your outstanding presentation, and look for, in the future to work with you again on your webinars. If CACA can help you or your company do anything, let us know. Second,
thank you very much.
Thank you very much. Thank all the audience for their passion and their time. And I like also to use this time to for the last thing I need to do is to do the poll questions. Let me see if I can pull it out. This is the first time I do that. Okay, so I don't know if can people see the I have to do launch. Okay, here you go. So there are a couple of pool questions. The first one is ACE master development kits are being sold at the list price for one column for 3, I guess. So what is the likability you can to purchase it? So there are 4 choices, and so if audience can just make the selections. Oh, great! It's 80 more than 86% of people say okay, they're going to buy your column. The kit. Okay, that
sounds great.
Yeah. Let me do the second one if I can do correctly. Let's see how do back to the second one again. Apologize, I'm doing this. I'm an amateur for that, obviously. If I can pull out the second one. Here you go. Okay. Which vendors columns do you use to develop your methods? Now, I think again, this is get a survey in terms of ideas. I think all of these vendors probably have very unique products you can use, and I guess that will be helpful for us to know how the industry is using the columns. Okay, and I think obviously we have more than 100%. I think it's just people are using more than one, I think, columns, and I think all the columns are very much used in the industry, and we have at least 50% of people using all of them. And with that, I again, thank you, Alan, and thank you, Jeff, for the sponsorship. And again, we look forward, to work with you guys in the future. And again, thanks to the audience. If you are interested in joining CACA, please sign up on the website or send us the information, or just come to the PICON or HPLC meetings. With that, I would like to close the meeting at this moment, and have a great holiday. Thank you.
Thanks very much, everybody. Goodbye.
Goodbye. Thank you.